Good morning. My name is Christina Margarita Charalampidou, and I'm a PhD student at the University of Aegean. The subject of my research work is the examination of a ternary cement-based restoration paste reinforced with carbon nanomaterials. Firstly, I will make an introduction to the scientific problem. Then I move on to the theoretical background. Next to the experimental procedure. And finally, I will present the experimental results and the conclusions. According to the literature review, cement is not the appropriate material for restoration because it is linked with many problems, such as production of salts, high stiffness and strength, setting shrinkage, and cracking. Some of the problems associated with the application of cement mortars can be seen in the picture. In order to exploit the advanced properties of cement and overcome the previous disadvantages, we apply lime cement materials that have already substituted the lime natural hydraulic lime mortars in restoration works. In order to produce composite materials with advanced physical properties, we exploit nanomaterials. There are different types of carbon-based nanomaterials available on the market, such as graphene and nanotubes, with unique combination of physical and chemical properties, thermal and electrical conductivity, high mechanical strength, and optical properties. Out of the different carbon-based nanomaterials, we chose graphene for the present work. There is a single atom thick sheet of hexagonally arranged sp2 bonded carbon atoms that is not an integral part of a carbon material, but is freely suspended or adhered on a foreign substrate. Dimensions of graphene can vary from several nanometers to the macro scale. It forms parallel levels. And there are many derivatives of graphene, but in the present work we used graphene oxide and reduced graphene oxide. The approach of our research work is the combination of carbon-based nanomaterials with the compatible matrix that we found in order to produce final composite material appropriate for damage monitoring. In this point, I would like to say that the present work is a part of a national research project named AKEISTHAI, that is a collaboration of different partners all over the Greece. Moving on to the experimental procedure, I would like to say that the first step is the mixing of the materials according to the ASTM C305 specification in order to be casted into molds. And afterwards, the maintenance of the specimens on water with calcium hydroxide for 28 days is following, and then follows the testing of the mechanical properties that consists of flexural tests, compression, and electrical properties. The materials that were used were cement, metakaolin, and lime, with a mixing proportion of 35 weight percentage of cement, 35 weight percentage of lime, 30 weight percentage metakaolin, and water to binder ratio 0.55. The GO and RGO were added at 0.15 weight percentage of the binder. It is important to point out that the concentration were not a random concentration, but were chosen according to preliminary dielectric spectroscopy experiments on their aqueous dispersions. The first step of the experimental procedure consisted of the flexural tests that were performed in an MTS inside electromechanical machine with maximum load at 10 kilonewton. Afterwards, the compression tests were followed. And finally, we measured the electrical resistance measurements with the 4-wire method. And the method for measuring the electrical resistance was the Ohm's law. The total time of measurement was 30 minutes. The electrical resistance was measured as the mean of the last 5 minutes of the total measurement. Moving on to the experimental results, we can see the flexural stress against the crosscut displacement of the three characteristic curves of the reference material, the matrix with GO and the matrix with RGO. The average flexural strength of the reference material was 2.40 with a standard deviation of 0.11 megapascal. The matrix with GO was 2.44 with a standard deviation of 0.18 megapascal. And the flexural strength, the average flexural strength for the matrix with RGO was 2.56 with a standard deviation of 0.13 megapascal. The results are summarized in the right figure, where a 14% increase of the flexural strength is noted for adding the GO, while a 6% increase were noticed by adding RGO. The same logic is followed in the compression test, where the figure of compressive stress against the gross displacement for the three characteristic curves of reference, the matrix with RGO and matrix with GO, are presented in the left figure. And the average compressive strength for the reference is 8.4 with a standard deviation of 0.42 megapascal. The average compressive strength for matrix with GO is 10.6 with a standard deviation of 0.53 megapascal, while for the case of RGO is 11.2 with an average with a standard deviation of 0.56 megapascal. The results are summarized in the right figure, where an increase of 29% was observed by adding GO in the matrix, while an increase of 33% was observed by adding RGO in the matrix. Moving on to the results of the electrical resistance measurements, the figure of the electrical resistance with time evolution is presented for the reference material, the matrix with GO and the matrix with RGO. Reference samples presented 1.04 mega ohm, while for the reinforced samples was for the RGO 0.52 mega ohm, and the resistance for the RGO was 0.33 mega ohm. By adding GO in the matrix, a decrease of the electrical resistance by approximately 68% was noticed, while regarding the RGO, the respective decrease was of about 50%. This electrical resistance decrease is beneficial for the development of self-sensing properties. I want to point out that such a small concentration of nanomaterials leads to such a large decrease of the electrical resistance. Reaching my concluding remarks, I want to point out that the addition of graphene-based materials allows for the increase in mechanical properties. The flexural strength increases by about 10%. Compressive strength exhibits an increase of 30%. Platelets, flakes affect mostly the compressive strength due to their microstructure. RGO decreases the electrical resistance by 50%, while the GO decreases the electrical resistance by almost 70%. This is attributed to the higher number of functional organic groups in the GO. The present work is a part of the national research work mentioned before that is co-financed by the European Regional Development Fund of the European Union and Greek national funds through the operational program Competitiveness, Entrepreneurship and Innovation. Thank you very much for your attention.